Thank you, everyone. Good afternoon. I must thank the organizers for giving me this opportunity to talk about our research at Raman Research Institute. Some of you will be visiting Raman Research Institute, I guess, in next few days. And today I'll be talking about a new experimental setup, what we are building in RRI. It's exceptionally new in the sense that we are just having our lab space ready. So this is an experiment on quantum gases with tunable interactions. Towards the latter part of this talk, I'll be also discussing about a non-perturbative measurement techniques what we are developing. I'll show you some data, mostly driven by Dibyendu, our theory friend in RRI. Okay, let's go on. Okay, so I just wanted to introduce our group members, Maheshwar, Bhagalakshmi and Sagar. They have joined the PhD program. Dhanalakshmi, Rohit and Dikshit, they are working as research assistant and MSc project students. They are all part of this exciting journey of setting up this new experimental setup. They are taking care of the laser system, vacuum system, and optics and all the other things. Okay, so this is a class of experiment which is motivated by like a lot of experiments in modern times. One statement of Feynman in his 1982 paper that one controllable quantum system simulating other, and then this is not really a very new concept. For example, various astronomy clocks which have been present in the world, like mechanical Prague astronomy clock, which has not really a direct connection with the astronomical movement of the celestial bodies, but it was fairly accurately predicting the celestial movement of the celestial bodies. Similarly, the philosophy is that you set up an experiment with ultra-cold quantum gases, and then you try to look for similarities of such system with other complex system in condensed matter system, and so on and so forth. So this is the driving factor in this kind of experiment. So with cold atoms, there have already been over the past 2 decades a lot of successful experiment which has been termed as analog simulators of various systems. For example, the seminal superfluid Mott insulator transitions, which is observed in MPQ already 1.5 decades ago by Emmanuel Bloch's group, BEC-BCS crossover, then also in the Dirac points in Fermi gas, in honeycomb lattice. One of the experiment I was part of where we look at the disordered interacting system in one dimension and try to look at transition from localization to delocalization transitions with ultra-cold atoms. 2D physics in 1D Tongs-Geradio gases, quantized vortices in fermions. And these are a lot of so-called condensed matter system which have been either for the first time observed or a very clear observation of the phenomena using the cold atom or quantum gases in such system. So the way to trap the atoms in periodic potentials is typically by using optical lattices. You create interference pattern of far detuned optical trapping light, and then atoms get trapped in the interference maximas and minimas, and you look at the effect of the condensed matter system where the atoms now mimics the electrons in optical lattices, and then the potential goes as 1 over detuning of the optical lattice. So detuning can be very, very large, so potential is low. And then scattering goes as 1 over detuning square. So the scattering by atoms is very low. So you can have almost a system which mimics condensed matter systems where ions are trapped in periodic potentials. So one way to look at it, like in condensed matter periodic potentials, we can have ultra-cold atoms far below the critical temperature. So there is no thermal motion left. And then one can have the quantum gases in optical lattices, which emulates the electrons in solid state systems. There is another interesting feature of such systems is that we can tune the interactions via so-called Feshbach resonances. So two-body potentials are like this, and very low energy atoms are still unbound or free particles, but you can tune the two-body potential by applying an external magnetic field, because these atoms which are in these systems are not, they have magnetic moments, and you can tune the two-body interaction, and you can actually bring the least bound state of two-body potential on resonance with the free atoms, and then by applying an external magnetic field, you can affect the scattering length, and so by affecting the scattering length, also the total interaction energy in the system. So this is a way of tuning the contact or on-site interaction energy in this kind of a system. So one of the ways to see that you have tuned the interaction energy, just looking at the Thomas Fermi profile of a Bose-Einstein condensate. In this case, the size of the condensate itself is proportional to the scattering length, and the total interaction energy is also proportional to the scattering length, which can be tuned using the external magnetic field. The scattering length becomes a function of magnetic field, and this is an external knob which you can tune in this kind of system, so that the interaction of on-site interaction can be tuned. Now, various interesting effects have been already studied with such contact interaction. One such effect was the direct ground state solution of the Bose-Hubbard model, so which is a famous system for solid state physics or condensed matter physics. So the effect is that when there is no thermal energy, you only have to worry about the tunneling energy between the adjacent sites, and which is captured in the first term, and then the on-site interaction energy, and there is an overall potential in these artificial systems usually, so that is captured by this chemical potential term. Now, if the on-site interaction energy is repulsive, if the tunneling energy is smaller than the on-site interaction energy, it will cost more energy to take an atom from site A to site B, which is of the order of U, and then if such a situation where the interaction energy wins, then such a tunneling will be suppressed. So one gets what is called a Mott insulator. And in case the tunneling energy is high, which can be tuned by just either changing the depth of such individual lattice site, then the system will be superfluid. So we can see a superfluid to interaction insulator transitions in this kind of system, which was seen famously by the group of Emmanuel Bloch in 2002, where they have looked at the loss of phase coherent going from the superfluid phase to Mott insulator phase. Okay, so this is so far about the neutral atom quantum gas simulations. I tried to say that there have been a lot of studies over the last couple of decades, but there are a few limitations of such systems. One is that we are talking only about on-site interaction energy, which goes as 1 over r to the power 6 potential, which is really short range. So the nearest neighbor or next nearest neighbor interactions are practically not present in such system. And very interesting effects like quantum magnetisms and so on are only probed by super exchange and exponentially small strength of the lattice depth, and this kind of a situation, which is rather artificial, and there have been some criticism that how can such systems then be a true simulator of condensed matter system where you have also long range interaction and so on. So there are possible solutions. One, there was a nice talk today morning about using cold ions, where the potential cold ion and ultra cold neutral atoms or ion-ion interaction, this kind of physics, which is captured by the cold ion physics. Also with Rydberg atoms, there have been long range interaction one can see. And then one possibility is using the ultra cold dipolar molecules. So I will try to say that this is the experiment we are setting up in RRI. So once you consider the dipolar molecules, which is created by heteronuclear atoms, and then if the dipoles are free in space, then the interaction goes as 1 over r to the power 3 minus 1 over r to the power 5. This d1 and d2 are randomly oriented. But once we apply an external magnetic electric field, and also once you consider these are the ground state molecules, so the dipole moment is also tunable because the rotational level gets mixed by applying external magnetic field. And then you get a 1 over r to the power 3 interaction when they are aligned parallel. And when they are aligned next to each other like this, then you have an attractive interaction, and this is repulsive. And this is really long range, 1 over r cube. And moreover, this long range interaction is also anisotropic. It depends the confinement. If it is two-dimensional confinement and if the molecules are oriented parallelly like this, then you have a repulsive interaction. And if they are aligned on top of each other, then you have a attractive interaction. So the external electric field, first of all, polarizes the entire sample of the molecules. And then I will come to this a little bit later. No, this is negligible. So this interaction, because the d square of external electric field, because as you can see that the dipole moment itself is a function of the external electric field, and because the rotational level of the rho vibrational ground state, that get coupled to give you a dipole moment. So this is one tuning, and second tuning is that this also orients, and you can apply the external electric field in arbitrary direction in space with respect to the confinement, which I will come to this in one or. Okay, so to create molecules and making them ultra cold going to degenerate state is not that straightforward, because molecular potentials are really a jungle. There are so many molecular levels and so on, and this is precisely the reason a direct laser cooling and trapping of molecule is not that straightforward, because you can, laser cooling depends on the close to 2-level approximation, and once the atom is excited or the molecule is excited, it can go to many of the rho vibrational levels, and then they can get lost, and there needs to be a lot of repumping lasers and so to say. So there are technical difficulties. But there have been experiments over the past decade. One famous experiment is from NIST in US by the group of Deborah Jean and June E. So they have created the potassium rubidium ground state molecules, ultra cold, very close to degeneracy. And also in the group of Innsbruck, in Rudy Grimm's group, they have created rubidium cesium molecules. There have been strong progress in the theory, taking care of the long range interaction and so on. And there are many other groups. I have not listed all of them because over the past few years, there have been really a lot of interest in this field to create ultra cold molecules and in degenerate regimes. So we have selected a system which is sodium potassium, and here to answer also your question, how external electric field tunes the dipole moment of the molecules. The dipole moment is 0 in presence of, which has to be distinguished with the magnetic dipoles. In case of magnetic dipoles, they are always present. In the electric dipoles, you can actually tune the dipole moment, and so to say the strength of interaction, not just the orientation. And then these so-called alkali atoms are workhorse of ultra-cold atom community, but not all alkali atom pairs, heteronuclear pairs, are chemically stable. So to say that the heteronuclear molecular potential is not less in energy than the homonuclear molecular state. So sodium potassium fortunately is one of the few which has the chemical stability and pretty high dipole moment, with a saturation dipole moment around 2.6. And then the degenerate sodium and degenerate potassium simultaneously is fairly relatively straightforward. And then there is also other interesting physics one can explore with such a system, not just molecular physics and long-range interaction, but also physics of Bose-Fermi mixtures. One can have a sodium, which is a boson, with potassium 40 and potassium 39, which are fermions and bosons respectively. So one can look at the physics of Bose-Fermi mixture or Bose-Bose mixture with this kind of system. And then one can look at so-called a dipolar length, which is of the order of more than a micron or 30,000 Bohr radii. And this dipolar length is important because this gives an effective length scale to the system. And when the atoms are trapped in artificial optical lattices, we use 1064 nanometer lattice laser, and where the lattice spacing is of the order of half a micron. So one can look at the next nearest neighbor and next to next nearest neighbor lattice physics. So our experiment is kind of designed to be following. We have cold atom sources, and they are captured in they will be captured in a three-dimensional dual species magneto-optical trap of sodium and potassium. Individual sodium and potassium sources are there, and then we will have a magnetic transport to a place with a better vacuum and high optical access to interrogate these atoms, and where we also have magnetic trap to evaporatively cool in the magnetic trap and reach simultaneous Bose-Einstein condensate and Fermi degeneracy of sodium and potassium. And then we also have Feshbach association, as I was explaining before, and then a 2-photon stimulated Raman transition to the ground state, where also external electric field will be applied to explore the long range interaction. So this slide I prepared for the students or people who are not in the field. So first step in this experiment is laser cooling and trapping. We have counter propagating laser beams from all plus x minus x plus y minus y plus z minus z direction. And then we also have a magnetic field in space to select the Zeeman energy levels. And then we can actually show that the atoms are cooled and simultaneously trapped towards the center of the trap with a temperature typically of the order of 100 microkelvin, which is still far above the critical temperature. And then it's of the size of several millimeter and between 10 raised to 9 to 10 raised to 11 centimeter cube. With the atom source, one can have a larger number of atoms in such magneto-optical traps. But temperatures are several 3 orders or more higher than the critical temperature to reach the quantum degeneracy in this system. So the next step is to transfer them in a dark trap, a pure magnetic or an optical trap. In our strategy, it is a pure magnetic trap, and then do what is called a evaporative cooling by selectively throwing out the high energy atoms from the trap and allowing the sample to thermalize to reach a Bose-Einstein condensate for the bosonic case or a Fermi degeneracy for the sodium potassium 40 system. And then using the Feshbach resonance to tune the interaction and also to create the lightest bound molecule which has a very, very low dipole moment. And then from such lightly bound molecules, one can do a 2-photon transition to go from the Feshbach molecular state to the absolute ground state, or vibrational ground state in the system. So this is the strategy we are following in this kind of an experiment. There have been, as I said, a lot of theoretical predictions about long-range interaction. One can look for paired superfluidity and independent superfluidity, and then also super solid phases. These are not really observed so far, and which is like a holy grail for such experimental system to unambiguously observe such kind of physics and so on. Okay, so I leave this part here, and then we also move to another topic, which is also driven by Dipendu here, is that once we have this kind of different quantum phases and so on, what would be the detection technique? So traditionally, how the cold atom or quantum gases are detected are using destructive imaging techniques with absorption imaging, near resonant, and then it's one shot, you take one picture of the system and so on. And one possible alternative, what we have been thinking about, also learning from the condensed matter community, is to do a spin correlation spectroscopy of this atomic system. And this work is in progress with Dipendu, Hema Ramachandran, and Shanita. So the idea here is that the polarization rotation in cold and quantum gases. This is a novel tool for non-destructive and non-perturbative detection. First of all, the probe itself is far off resonance, and then it detects only the phase of the light with negligible scattering. And atomic polarization fluctuation is an intrinsic property, and through many body physics can be probed. And in this talk, I will be talking about development and understanding of this technique as far as we are concerned using thermal atoms, because this is the system we are looking at. And there have been recent interest in this technique, especially mainly from the condensed matter community. So in just 2 seconds, the Faraday rotation is very well known to everyone. You pass a linear polarized light through an active medium with a collinear magnetic field, and because of the collinear magnetic field, you can consider the linear polarized light composed of the left circular and right circular polarized light, and these two components are shifted in frequency space in left and right, and then when they overlap after coming out of the sample and interfere to give you a linear polarized light again, which is rotated, and the rotation angle of the linear polarized light is given by also proportional to the magnetic field. This is fairly familiar with everyone. So what we are looking at is that even at zero longitudinal field, when there is no polarization rotation is present, atomic polarization can fluctuate due to its relaxation at thermal temperature, and then fluctuation of population between different magnetic states will give magnetic circular birefringes, and in turn a fluctuating probe beam polarization angle if the probe is far off resonance. And then these polarization fluctuations will eventually give rise to a fluctuating output polarization, and which is completely a phase fluctuation, so to say, and we can detect such phase fluctuation in polarization measurement. And then we can connect the response of a system of small external perturbation with a spontaneous fluctuation. And even though the average of the polarization is still zero, the standard deviation of the polarization, which is the spin correlation power or spin noise power, it is non-zero. And then by Wiener-Khanchin theorem, we can say that if you take an autocorrelation in the time domain, is same as the power spectrum in the frequency domain. So the task is really to look at the power spectrum of the polarized output polarization fluctuation in our case. So one experimentalist's way of simplifying this system is that I told about non-zero field, but one can apply a perpendicular field. So still it is zero field along the direction of k vector, but by applying a perpendicular field, we can shift the noise peak to the Larmor frequency, and then because we shift to a higher frequency, it's easier because 1 over f noise falls off as we go away from the DC to measure the polarization fluctuation noise itself. And then we do the Fourier transform of the autocorrelation function, which will give us a Lorentzian peak centered at Larmor frequency with the width which is 1 over the relaxation time of such system. And the spin noise amplitude is 1 over delta. Delta is the detuning of the probe beam and proportional to square root of the number of atoms in this kind of a system. So this has to be, so this is 1 over delta, whereas scattering goes as 1 over delta square. So if we are sufficiently far off resonant, then the perturbative scattering is negligible, and we are mostly sensitive to the spin noise itself. Okay, so the experimental setup is we have a nicely shielded situation system with rubidium 87 atoms with a perpendicular field whose magnitude we can vary, and we send a off resonant probe beam whose frequency also we can vary, and then at the output we do a polarimetric measurement where we are only sensitive to the polarization fluctuation between the two arms. So all our detector is such that the common mode rejection takes care of the natural intensity fluctuations or the absorption and so on. So what we will be detecting is purely polarization fluctuation. So this is the system. So now this is our measurement. So we look at a spectrum And then one of the first thing we notice is that this is noise spectra. Of course, the signal is very, very low. It's a nanovolt per square root of Hertz regime. But the signal to noise is rather good already because our background noise level is pretty low. We take care of our intensity and the polarization fluctuation of the laser beam. And this is really the noise signal which is coming from the polarization fluctuation of the system. And when I say polarization fluctuation, this actually means that the fluctuation of the population between different MF sublevels of the atom. So I will identify the peaks later on. And then first thing we notice is that the width of this signal is extremely narrow, of the order of few tens of kilohertz, which is much smaller than the Doppler and pressure broadening and even natural line width for optical transition. And this is also in some sense a high precision detection. So when we had this rubidium cell, we were said that this is a pure rubidium 87 and our optical absorption detection, we don't see any signature of rubidium 85, but the noise spectra showed up even at the 1% level, small quantity of an isotope abundance of rubidium 85. So, people thinking about applications and so on, this kind of techniques can be also used as a isotope abundance test and this kind of thing. And this line width is a pure noise spectra and it's independent of the probe laser line width. And I will talk about identifying the different spin fluctuating states. So I said that we apply the perpendicular magnetic field for a reason of convenience. We want to go out of the noisy region because the background noise is 1 over f kind of a signal, but it also gives us a way of measuring precisely measuring the magnetic field if you don't know that, or if you have a precision measurement of magnetic field from some other way, then just by looking at the shift of the Larmor peak, which now we can detect with good accuracy, also tells us a rather good measurement of the G factors of these atomic transitions and so on. Just wanted to mention this nice strength of this kind of measurement. And then as we apply higher and higher magnetic field, we can also start to see that the inter-Zeeman splitting in the noise spectra, and then clearly see the quadratic Zeeman effect. And if you now plot the separation of different spin noise signal, one can actually find a nice curve with the Zeeman energy separation versus magnetic field, and we get a hyperfine constant with less than 1% accuracy already with this very simple measurements, so to say. Moreover, once we apply even higher perpendicular magnetic field, we can actually see that small contribution of energy separation because of the nuclear Zeeman contribution in such a system. And just by measuring the separation of the f equal to 1 and f equal to 2 hyperfine state spin fluctuations and the separation between them, we can measure fairly accurately the nuclear Zeeman GI. And this also is not very, very off for a given system and within the error bars of our experiment. So one thing is that we can already have so in principle this is one typical data where we have all the spin state fluctuating for f equal to 2 different MF state spin fluctuation and f equal to 1 the correspondingly 2 MF state transitions. And then we can actually optically pump using a strong pump beam, doing a pump probe kind of an experiment by optically shelving all the atoms from f equal to 2 to f equal to 1 state. We can actually recover just purely f equal to 1 spin fluctuation and doing vice versa by optically pumping all the atom from f equal to 1 to f equal to 2. We can have all the f equal to 2 spin state fluctuation. And we can also have partially polarizing the atoms and have a detection. So this is a way of spin state selection and spin state identification just by doing this kind of non-perturbative measurement. And these kind of measurements we are interested to do because we want to do all these measurements with cold atoms later on. And with thermal gases, we already have a lot of interesting signature of this kind of. So now spin noise amplitude we have actually probed with the probe beam detuning varying, just to understand when we are going from the non-perturbative regime to where we get the perturbation. And the probe beam itself changes the spin population in our system as you saw in the previous data. And then we can model such an spin noise amplitude, including also the optical pumping effect and spin polarization effect. And this is really a model without any free parameter, and our data matches with such a system. If we go far off resonance, like in typical condensed matter experiment, what we will do, then we recover the 1/delta behavior. That once we come closer with the probe beam detuning, then also the atomic physics, optical pumping effects are important and no longer can be neglected. And what is important is that if the probe beam has a strong power, so this can change the spin population of the system itself. So this we see in the spin noise amplitude versus the probe power kind of measurement. So we can say that for a small probe power, we recovered the intrinsic or unperturbed noise amplitude. And also if we vary the number of atoms in our experimental setup, so the noise amplitude really goes as square root of n, which one would expect that this is purely a random noise, not a correlated signal coming from the situation. And similarly, if we want to say that whether we are really at the regime, because this width of the signal itself is a direct measure of the spin relaxation time in these cases. And then if we are several gigahertz away with our probe beam, we already detect the spin noise width to be at the intrinsic level in this kind of a system. And similarly for the probe power. So we just got started with some measurement with cold atom. So right now we have a situation where we just wanted to look at the polarization rotation itself. We let our cold atom, which we have a rubidium-87 cold atom system, pass through such a polarimetric measurement system, and we apply a collinear magnetic field where we indeed see the polarization rotation itself. And this itself is an interesting to many groups now, because just looking at the polarization rotation and going far away from the resonance, or a few megahertz away from the resonance already with cold atom, one can be in a non-perturbative regime. But these are static measurements. So one is looking at the just the atoms, the detection of the atoms without perturbing them. But once we go ahead and try to look at the noise of the polarization fluctuation in this system, we are also planning to make more statement about the statistical fluctuations of, or the so-called dynamic measurements in this kind of a system. So just wanted to conclude, and so we are setting up a new experimental setup to investigate the quantum gas mixtures and also with long range interaction. And this experiment, the focus will be to do analog simulation of condensed matter system mostly, but it's not limited to only these. There are large range of experiment one can look at, and also we are simultaneously trying to develop a novel non-perturbative detection technique for the cold atom. So far I had shown you some result for the thermal. This one, we allowed just the MOT to drop through the probe beam. It is still at a temperature of 150 microkelvin. And the only thing is that we took care that there was no stray magnetic field, everything was switched off by the time the cloud is falling through this probe, and we did this polarimetric measurement. So we took care that there is no other fluctuation, and which we are detecting. We are purely detecting the polarization. But, well, here we are not detecting fluctuation yet. We are looking just as a polarization rotation. Oh yes, sure. Yeah. From here we already from the total polarization rotation, it agrees well with our absorption measurement of the total number of atoms. Yeah. So So there are various proposals. Means one is to look at dissipation in such systems. For example, also the, because it's not really considering that you have a cold atom trapped forever in an optical lattice potentials and so on. There is also noise and so on. One of the reasons why I wanted to connect also this polarization fluctuations kind of measurement, that once you consider, let's say, spin wave in such a system, you flip a spin and see how the spin wave, for a closed system, the the signature will be very different than a case where dissipation is also taken into account, and which can be tuned. You can actually, like interaction, one can also add disorder and then look at the disordered interacting system. So there are various experiments where one is not just looking at Anderson localization, but also using tunable disorder with the interacting system. So where you are looking actually at time scales of how the system goes from a localized to a superfluid. Well, see, there is one thing is the total noise. There is also another. First of all, the numbers are comparable, because once you have this focused probe beam through the through the thermal atoms, and when you have the same probe beam through the cold atom, because of the densities, the number of atoms which you are probing are similar. But what you can yeah, and in mod also not very different, no? Oh, okay, no. So for our experiment, we are actually having a multiple path through the cold atom. So it's not just one single pass. So this is one aspect, and the mod is of the, so far the first measurements are planned to do in mod is of the order of a millimeter. And here in the vapor also, our Rayleigh length of the probe beam is few millimeter only. So it's not very different. So that way is fine. But one issue is that as we go down in temperature, so then of course you lose signal. But one thing what we are discussing is that also the spin relaxation times are going to be very, very long. So in that case, you will have a integrated signal which is low, but the peak of the spin noise signal will be high. So we are working on that. It's not that the first measurements of the polarization rotation itself otherwise would have given us a noise signal simultaneously, but that's very much a work in progress.